there is no room over here. So, what we did is we sort of gave a very precise mathematical way of arriving at this constraint. Okay. There is actually there's a intuitive way of arriving at this, which is more sort of more fun than what we did, right. So, for doing this intuitive way of arriving at the stability criteria, what I will do is I will draw a simple 1D grid, right. Our leapfrog scheme is what we have been talking about. So, our grid, this is my space, okay, and this is my time. On this I am considering, so this is my EZ I minus 1, this is my EZ I, this is my EZ I plus 1. What other variables are needed? E and H, okay. So, remember in time also the variables are staggered by half a grid, and in space also, right. So, this is going to be my H, let us call it some Hy, okay. So, Hy at I minus half, and correspondingly there will be a Hy of I minus, sorry, this will be I, yeah, this will also be I minus half, okay. In terms of time instance, this is say n, this is n plus half, and this is n minus half, okay. So, I have taken just Ez and Hy, okay. So, the TE polarization, I am just looking at one of these equations, okay. So, so I mean the differential equation for this was mu naught dHy by dt is equal to by tau x, right. This is Tm case. Tm case, this is the equation that I had, right, Ez Hx Hy. So, the equation for Hy was the following. Right. What do we do now is, so this is my delta x is this, okay, and delta t is this whole thing over here, okay. So, let's write it in stepwise form. So, Ez is spaced apart by delta x, you already know that. What is the next thing? So, what is the time required for the signal to go? So, time required, physical time required for signal to go from I minus 1 to I. Imagine there is a physical wave that is propagating in space and time. What is the minimum time required for the wave to go from I minus 1 to I? So, what is the distance? Distance, why is it 1? Distance is delta x. What is the speed at which this wave can go at as fast as possible? C. Right. Now, the third point we can say is that minimum, so I am calling this minimum is tau, okay. This value of delta x by c is the minimum time required for the signal to go from here to here, right, from left to right, okay. Now, we can say that before this, before the lapse of tau, I should use my update equation. What was my update equation? So, just look at this equation on top over here. I can write Hy n plus half I plus half is equal to Hy n minus half I plus half minus 1 by mu naught Ez I minus Ez I minus 1. This was my update equation, right. So, what all values are involved in evaluating H at n plus half? It is Ez here at I minus 1, Ez at I, and Hy at the same location in space, but a different time location, previous time location. Okay. Now, this minus, oh, there is a delta t over here. Okay, this is the equation. So, now before this period of interval tau goes, I should use my update equation. Why? Because if I do not use this update equation, then this guy over here, Ez I, would have got a new value. So, I am using the update equation, but the value inside it is wrong. I would be using the past value of Ez over there. I do not want to do that. So, before the wave has physically gone, I want to quickly use my update equations while my variables are still faithful to the physics. My variable says Ez I minus 1, all at some time instant n and n. So, when I substitute the value inside these things, it should be actually the value of the field at those times in points in space and points in time, correct? Not if I wait for more time, I will use this formula, but the numbers that I put inside will be wrong because they will refer to old information. Wave has already travelled physically. So, I want to do in some sense, it sounds very grand when I say it, I want to do a faster than light calculation. Before the light gets there, I want to use this update equation, right. So, that basically says that the times, so this implies that the time step should be greater than or less than this tau, less than tau. Right, and is that's exactly what we had earlier, right? Delta x by c, yeah, I mean it's a very fine yeah. So, the time step has to be, so I mean we usually think that c is a very large value, so delta x by c is going to be a very small value, right, but that is not exactly the right way to think of it. The correct way to think of it is, imagine there is a wave at a constant frequency omega, right. So, that omega I can write as 2 pi by t. So, what we should actually be looking at is the comparison between delta t and this time period t, capital T. That will not turn out to be such a drastic number. Okay. For example, supposing you are in optical frequencies. Optical frequencies, what is omega? Okay, forget optical frequency. Let us say you are at microwave, 1 gigahertz. 1 gigahertz is 10 to the 9, right. So, what is the time period there? 10 to the minus 9, and 1 by c is going to give you what? Again small numbers, right. So, delta t looks like a very small number, but when seen in relation to the time period of the wave, it is not going to be some microscopic fraction. Okay, so this is the intuitive way of arriving at this stability criteria. Yes, the third part again. So, first part is clear, space the Ez is apart by delta x. Then we are saying that in this equation, when I want to update Hy, okay, so I want to update this guy. What all do I have to use? So, I have to use this guy and this guy as per the formula. Now, when I am going to use these equations, these had better represent my current estimate of these quantities. Sounds obvious, but of course, they should be current. But if I wait for a time greater than delta x by c, then the wave has, which is let us say in one case travelling from left to right, the wave has already travelled from Ez I minus 1 to Ez I, it has physically travelled. But I did not, since I have not yet done a time update, my variables still contain the old value. In the location of Ez I, it still has the old value because I have not done a time update. So, when I go to use the equation, I am using an older outdated version of Ez I. In order to prevent that, I should quickly do the update before the wave actually reaches there. So, when I use the equation, I am using the actual value that I know, my best estimate. So, says delta t should be less than tau. Okay. So, depending on your, So, this is a sort of a thought experiment, it is only a thought experiment, right. The wave is traveling through free space, we are just saying how quickly can I simulate everything such that I am being faithful to the variables that I am writing on my, of course I am not sitting there and waiting for light to travel and, right. So, this is all what Einstein would call Gedanken, right, thought experiments. Fine. So, what is nice about this stability criteria being derived in this what we will call an intuitive way is that it is very easy to generalize this idea to higher dimensions. Okay, 1D is fine. A question you can ask is in 2D, is the Courant stability criteria the same, right? So, here you will find factors of root 2, root 3, etc.